Hi, AP Chem students. This is a class video for Monday, May 10th, 2021. We went over some review problems. We went over the Voltaic cell worksheet, most of it, looked at an example of a Voltaic cell, and we also went over some practice problems, which were on Kahoot. Homework is to do the review FRQs and MCQs, the second set, and there will be a practice quiz tomorrow on electrochem and stuff from the review problems. And make sure to watch the video on the Nernst equation. We're going to be using it tomorrow. So our objectives are to label a voltaic cell, or also known as a galvanic cell, to identify the half reactions in the cell and to calculate the standard cell potential, and design a galvanic cell given a list of half reactions. So the first thing we have to understand is that we have some important units that are used in electrochemistry. The first unit is called the coulomb, and we have heard of this through Coulomb's law. Coulomb is a person, and we named this unit of electrical charge after Coulomb, and one electron has a charge of 1.6 times 10 to the minus 19th coulombs. So if we take a mole of those, if we multiply this number by Avogadro's number, we get Faraday's constant, which is an important constant, and gives us the charge on 1 mole of electrons. It's important to know the charge because once we have these electrons moving through a wire, let's say, if we know the rate at which this charge is moving through a wire, we will know the current, and we can determine how much electricity we can get out of a certain reaction. The potential difference is the difference in potential energy in terms of electrical charge. So the difference in electrical potential from one substance to another, or in one area, one point in a substance to another point. And so there is this difference in potential. If we have no difference in potential, then charge can't flow. It's when we have potential differences that we can have electrons flow and we can get a voltage from a reaction. So 1 volt is the potential difference that will give 1 joule of energy to a charge of 1 coulomb. So if we have a charge of 1 coulomb, it will give us 1 joule of energy, and that is defined as the 1 volt potential difference. Okay, and so you can see here the conversion here. 1 volt is 1 joule per coulomb. And then finally, the current I, okay, and make sure this is I and not L, okay. I is the amount of charge passing through a wire or a substance per unit time. And this is measured in amps, okay, or capital A. 1 amp is 1 coulomb per second. And on the equation sheet, which we're going to look at in a second, I, the current, okay, is Q over T, where Q is the charge and T is the time in seconds. So where do we find these equations on the equation sheet? Right here. Okay, so you can see here in the thermochem, we've got delta G and how it relates to the cell potential, E cell here. We have the current equation. Okay, so we have the free energy. And how you can get that from E cell. Okay, here is how we can relate current to charge, okay, and ultimately to the moles of electrons in a reaction. And here, this bottom equation, which we'll talk about tomorrow, is the Nernst equation. And our old buddy Q, the reaction quotient, is in the Nernst equation. Over here on the right, they define a bunch of things for you so that you can use this to refresh your memory. They give you Faraday's constant right here, and then they give you the conversion of volts in terms of joules per coulomb. All right, so how do we get these voltage values? So we have tables called standard reduction potential tables. And these tables show a bunch of half reactions as reductions, okay? These are all written as reduction half reactions, and the voltage for that half cell, that half reaction, the potential for the substance to be reduced is given here, over here on the right-hand side. Okay, so these are all substances getting reduced because we're adding electrons to them, and that reduces the substances. And you can see that the most positive here is fluorine gas. It loves being reduced. It is very thirsty for electrons. Okay, it has a strong desire for reduction, and so it has a very positive reduction potential. I should also mention that this is not the end-all table. There are many more half reactions that are not given here, that you can get them in the back of your textbook or on the internet, but this is not an exhaustive list. Now, in the middle here, you can see that the potentials slowly drop as the substance is less, okay, inclined to get reduced until we get to this hydrogen standard. Okay, this is the reaction for the hydrogen standard electrode. Okay, actually, usually it's abbreviated standard hydrogen electrode, SHE, SHE, and so you can see here that it's defined as 0. All of the reduction potentials are based off of this hydrogen standard electrode. Okay, so what you'll see in the next few slides with the cells, you make one of these half reactions in the electrochemical cell, the hydrogen electrode, and then you put one of these other substances as the other electrode and measure the potential difference between the two. And that will give you the reduction potential. The difference between them gives you the actual reduction potential. Okay, but these are all based on this standard hydrogen electrode. Now, you can see below hydrogen, now the numbers become negative as the substance does not want to be reduced as much, but is more likely to become oxidized. So down here, lithium, it wants to stay oxidized, okay? It would like to be oxidized over anything. So here, it does not actually want to do this process, but it actually wants to do the reverse, okay? So now, if we pair something that wants to be oxidized with something that wants to be reduced, we put those two reactions together, we have a redox reaction that happens spontaneously, that is thermodynamically favorable. And so that's what we have here in this voltaic cell diagram. Okay, so red cat and ox is a way to remember that reduction happens at the cathode. At the anode, we have oxidation. And you can see here the flow of electrons, right? The zinc gets oxidized. Electrons travel up the electrode to the wire, okay, to the cathode. And at the surface of the cathode, the copper is getting reduced. The copper ions turn into copper solid. And so this electrode, this cathode, gets larger and larger as time goes by, and this zinc electrode gets smaller and smaller as time goes by, because all of these zinc ions, right, they are going into solution. So this electrode is losing mass. This copper electrode is gaining mass. And so electrons flow this way. That makes this side, okay, it starts getting negative in charge. So to replace, right, to make charge balance so that the electrons continue to flow, right, positive potassium ions, okay, K plus, come down the salt bridge, okay, and neutralize the electrical charge, right? They make the charge neutral again so that electrons can continue to flow, okay, from one from the anode to the cathode. And it's always the anode to the cathode, and the positive ions go to the cathode. The negative ions here, the Cl minus, are going to go to the anode to make the positive charge that's forming here on the left side, and balancing out the charge that way. And so that allows the electrons to continue flowing. Okay, so if there was no salt bridge, if you took this out, the voltage would be 0, because the electrons would get here and they get stuck. They pile up, right? And there's no way the charge would just build up. One side would become negative, one side would become positive, and then it would stop, because there's no way to continually get the charge to move unless you have this charge get neutralized so that more electrons can come down and reduce more copper. All right, so hopefully that helped in terms of an explanation of what's happening in the cell. And this is happening spontaneously. Okay, so this is a spontaneous, okay, or thermodynamically favorable. This is a mouthful. Okay, thermodynamically favorable. This happens on its own and provides energy through this redox reaction. So here, just in terms of questions, which metal is being oxidized? That would be the zinc, as it's labeled here. The metal with the larger reduction potential will be reduced at the cathode because of red cat. Okay, the metal that's oxidized, and ox, okay, is the anode. And electrons always flow from the anode, where oxidation occurs, to the cathode, where the electrons reduce the substance. What metal is produced at the cathode? That would be Cu. Will the voltaic cell operate if the salt bridge is taken out? No. Okay. Charge will just get built up. No, there's no way to neutralize. No way to keep the charge flowing. Okay, charge cannot flow if, right, we don't actually make the charge neutral so that the process can continue again. Does the zinc rod on the left get smaller or larger? Well, it gets smaller. Okay, zinc from the electrode turns into zinc aqueous ion in solution. It dissolves into the solution, and the zinc electrode gets smaller. All right, so then our E cell, this is our standard voltage produced by the cell. And by standard, I mean there are some conditions that have to be met. Okay, so we need 1 molar solutions. We need the pressure to be 1 atm. Okay, and we need the temperature to be 25 degrees C. So that refers to standard voltages given these conditions. Okay, so the metal with the higher, more positive reduction potential is the one that gets reduced. So here, if we look here for that cell, if we look at the 2 reduction potentials, right, this is the more positive one. And based on the cell, right, we know that this is the reaction happening here, okay? And then this, right, this is actually the opposite reaction is happening for the zinc. It's turning into zinc ions and getting oxidized. Okay, so what we do to calculate our E cell, okay, I'll put it up here. So E cell is equal to the reduction, okay, minus the oxidation. So our reduction potential is 0.34 volts, okay, minus the oxidation, which is minus 0.76 volts. Okay, so then when we do the math, we get 1.10 volts. Okay, so there's E cell. If we had these at standard solutions, okay, 1 atm, 25 degrees, then we would get 1.10 volts of potential difference. Okay, we'd get that potential from that electrochemical cell. How do we know if it's thermodynamically favorable or unfavorable based on the sign? This is positive. A positive voltage means that it is thermodynamically favorable, okay? So positive means thermodynamically favorable, okay? Positive E cell. Now recall that delta G negative, okay? Negative is thermodynamically favorable, okay? Negative delta G. Okay, so negative delta G is thermodynamically favorable. E cell positive means it's thermodynamically favorable. How do we know which metal gets oxidized and which metal gets reduced? Again, right, it's the more positive, okay, that gets reduced, okay? More positive reduction potential. And this would be more, we'll just say smaller reduction potential. Okay, so when we know which one has a larger one, we know that's the metal that will get reduced. All right, so Isaias and I set up this cell. Okay, we set up this solution was 1 molar copper sulfate. Actually, our cell was slightly different. We actually used copper nitrate and we used zinc nitrate. And they were both 1 molar. And so when we took these two, we expected a E cell, a standard cell, that was plus 1.1 volts. Now, in actual, when we actually measured this, okay, over here, was about 0.93 volts. Okay, so a little different, okay. It's off by about 0.17. Okay, so it's not the same. Well, there are many reasons for that, right? The salt bridge was a paper towel. Okay, so we're kind of getting some losses right there. Another thing, okay, there was oxidation on the metals. That zinc might not have been pure zinc. The copper might not have been pure copper. Okay, so purity of metals is another thing, right? If there was some alloying happening, then, okay, we could have had some other metals that might have been oxidized or reduced in place of these things. The other thing is, right, we were not at standard conditions. So, and I forgot to mention this one, but we are not at standard conditions. So if we're not at standard conditions, right, we can't actually expect to get the same standard cell voltage as the one published in our reduction potential table. So getting 0.93, that's a decent match, even if the temperature was not the correct one, or the atmospheric pressure was not necessarily 1 atm. But you can see that we're not getting something that's completely off the mark, and we are getting some voltage from this cell. All right, and then the second part of the worksheet was another electrochemical cell. And we've got here aluminum and lead. Okay, so first part asks which is the more easily oxidized metal, aluminum or lead, which is getting reduced. So we've got to look for these two reduction potentials. Let me find them both. Here's lead. All right, and here's aluminum right here. And then I look, which one's more positive? Okay, this one, the lead is more positive. This is going to get reduced. Okay, the lead will be reduced. The aluminum will get oxidized. So which is more easily oxidized metal? That would be the aluminum. And which is getting reduced? That's going to be our lead. All right, number 12 asks, what is the balanced net ionic equation showing the spontaneous reaction that occurs? So if we look here between lead and the aluminum, right, we're going to, because of the electrons needing to be, right, we need the same number of electrons reducing as being released through the oxidation, right? So this is going to have to go times 3, and then we will have to flip this reaction, okay, and take it times 2. So let me write these reactions below here, okay, because we don't have space there. So our reduction equation is going to be 3Pb 2 plus 6 electrons, 3Pb solid. Okay, our oxidation half reaction, right, we have to flip that and multiply by 2. So 2Al solid goes to 2Al3 plus and plus 6 electrons. Okay, and then when we add these, those cancel out. And so our net ionic, this is number 12. Our net ionic is what we get when we add these together. We get 3Pb2 plus 2Al goes to 3Pb plus 2Al3 plus. Okay, so there's our net ionic there. All right, so 13 says, what's the maximum standard cell voltage that the above cell can produce? Right, we take our E cell to get our E cell. Right, that's what the standard cell voltage is asking for. That's going to be our reduction potential minus 0.13 volts minus the oxidation potential 1.66 volts. Okay, so then when we take minus 0.13 plus 1.66, we're going to get 1.53 volts. Okay, there's our standard cell voltage. What's the direction of the electron flow in the wire? So remember, the aluminum's getting oxidized. Okay, so this is the oxidation, the anode, and the lead is getting reduced, the cathode. So here in the oxidation, we are producing electrons, right? So we're going from Al solid to Al3 plus, that's the oxidation, plus 3 electrons. So the electrons are being produced here. They travel up the wire, they go through the wire, they go down, and they reduce. Okay, so the electrons are going this way. What is the direction of the positive ion flow in the salt bridge? So if the electrons are going this way, this cell is becoming more negative, okay, more negatively charged. So in order to balance out the negative charge, we need positive ions, okay, flowing down and keeping the charge neutral so that electrons can continue to flow. Okay, so this is to the right. Electrons are also to the right. Okay, so which electrode is decreasing mass? Again, this is going to be the aluminum, right? Because that's going into solution. Which electrode, that should have been electrode, is increasing in size? That's lead. What is happening to the concentration of the aluminum ions on the left-hand side? That concentration of Al3 plus is going up. Okay, the concentration of lead ions, okay, Pb2 plus, is going down. Okay, and then we had to calculate the free energy change, delta G, for the cell. So there is an equation, delta G minus NFE, and you do not need to memorize this. This is on your equation sheet. The number of, okay, moles of electrons transferred. Okay, that is what N is. F is Faraday's constant, 96,485. Okay, coulombs per mole. And then here's our E cell from before. That was 1.53 volts. Okay, so if you check the answers key, I believe the answer comes out to 886 kilojoules, okay, per mole reaction is going to be your, and this is going to be negative, your delta G for the reaction. So that is a brief overview of voltaic cells. Okay, we'll look at probably another example tomorrow that you'll get to diagram and answer questions about. But if you have other questions about voltaic cells, and if there's something you don't understand with this voltaic cell, please email me or ask in class.